Smart cruise control, like that being demonstrated by Eaton Vorad, an associate participant in the consortium, is an example of a building block technology across the variety of scenarios. Another way these technologies can function as a system can be seen in the free agent scenario.
The whole idea in the free agent scenario is to put as much of the intelligence as possible right onto the vehicles. This has a bunch of consequences. First of all, we don't have to do any modifications to the infrastructure. Our sensors can pick up the markings that are already down there. Secondly, our vehicle is self-contained, so it doesn't have to talk to other vehicles, so we can run it in mixed traffic, even if there are human-controlled vehicles mixed in with the automated vehicles.
The work of the consortium indicates a combination of these approaches will lead to a fully automated system, one where drivers can choose to enjoy the scenery. What Demo 97 may lead to is an AHS prototype that can overcome many transportation challenges and double or even triple the flow rate of vehicles per hour.
10 years down the road from now, we'll have the actuators in place, we'll have many of the sensors in place, and it will just take a little bit of additional electronics, a little bit of computer programming to make it possible to have completely automated travel.
The platoon scenario is designed to show how vehicle automation technology can significantly increase the throughput of a highway lane. This should greatly reduce highway congestion by making it possible for each lane to carry considerably more traffic than a lane can carry today. The fully automated travel of the AHS vehicle relieves the driver of the chore of steering, so that driving stress is relieved, and it becomes possible to spend travel time doing what you want, whether that be work or leisure activities. The high-performance automatic steering system gives a very smooth ride, with more accurate lane following than even highly skilled drivers. The vehicles also control their speed and spacing automatically, making it possible to maintain much closer spacing than normal human drivers can, while remaining safe. The spacing control is so accurate that the driver and passengers cannot detect variations in the spacing while traveling under automatic control, even while going up a relatively steep slope. This accurate control gives the sensation of a mechanical linkage between the cars, which increases the sense of security and comfort of the riders in the vehicle. Viewed from the outside, the separation between vehicles looks closer than most people would generally expect to like. However, the accuracy of the spacing control leads to people quickly becoming comfortable with the close spacing. All of the vehicle maneuvers are automated, including the lane changing. This makes it possible for vehicles to enter and leave the automated lane or an individual platoon entirely under automatic control without imposing any tasks or new skills on the driver. The communication between vehicles provides complete coordination of these maneuvers to make sure that they occur at the right time and place. The platoon join and split maneuvers are the other maneuvers needed to form and separate platoons, and these are also done completely automatically. The rate of change of spacing is carefully controlled to make sure that these maneuvers feel smooth, natural, and safe to the vehicle occupants. The Delco Electronics video screen in the instrument panel tells the driver what the automatic control system is doing at all times, so that any unexpected maneuvers or changes in vehicle behavior do not surprise him. This helps make the automatic driving experience feel more natural and reassuring. The driver can choose to watch the display or ignore it. The activation and deactivation of the automatic control systems are done using the buttons mounted on the steering wheel, just like cruise control or radio control buttons in some of today's cars. This also helps make the automated driving experience seem more natural. There are a variety of special features built into the Buick LeSabres used for the platoon demonstration in order to give it the capability for automated driving, as shown schematically in this cutaway view. Some of the systems, such as the electronic steering actuator from Delphi Saginaw and the electronic brake actuator from Delphi Chassis, are not visible at all, even when you look under the hood of the car. The distance to the vehicle in front is measured using this millimeter wave radar sensor from Delco Electronics. This stepper motor mounted directly to the throttle body of the engine, which can very quickly adjust the throttle angle, controls the engine speed. The communication of data between vehicles is done 50 times per second by this radio transceiver system, developed for Hughes by Utilicom. Vehicle-to-roadside communication is done by this transponder from Delco Electronics, based on a system developed for electronic toll collection applications. The vehicle's position relative to the lane center is measured by these fluxgate magnetometers mounted under the front and rear bumpers of each car. Using software developed by the California PATH program, they detect the magnetic fields of cheap, permanent magnets that are buried every 4 feet along the center line of each lane of the I-15 HOV facility. Even this early installation of the magnets was done for a cost of only about $10,000 per lane mile, which is much cheaper than the millions of dollars it costs to build a new lane mile. The brains of the vehicle is a single Pentium computer, no more powerful than a laptop PC. It is mounted in a rugged chassis for experimental purposes. The computer uses the QNX real-time operating system and control software developed by the California PATH program. Although it appears as there is a lot of extra equipment in the trunk of the demonstration car, this could all be shrunk down to a small size for a production vehicle, so it will still be possible to carry a full set of luggage and golf clubs in the trunk of your automated car. The vehicles had been tested extensively before being used for Demo 97. This testing has included much more severe operating conditions than we ever encounter on I-15, as shown by this footage. These automatic steering control tests were performed at lateral accelerations of up to 0.6 G, which is much higher than you would experience in normal driving, to prove that the steering control system maintains very accurate lane tracking even under these extreme conditions. The technology that we are demonstrating on the Platoon vehicle has been under development for nearly 10 years and is based on extensive experimental experience by the PATH team, together with their partners from General Motors, Delco Electronics, and Hughes. The first PATH experiments using the magnetic lane reference system for guidance were conducted in 1989 and were followed by closed-loop steering control experiments on several test vehicles from different manufacturers, beginning in 1992. These vehicles have been tested under a variety of abnormal operating conditions, including partially deflated tires, wet, snowy pavement, severe crosswinds, and missing magnetic markers. The PATH experiments on vehicle follower control of platoons have been conducted since 1991, again using a variety of vehicles and technologies. The earlier experiments were conducted at relatively large spacings, 30 feet, but as the technology was improved, it became possible to operate at smaller spacings. In the summer of 1994, PATH and Caltrans researchers gave demonstration rides to a number of invited visitors here on I-15 in a platoon of 4 vehicles operating at 13-foot spacings, using engine speed control only. Later, with the addition of brake control, they were able to decrease spacings to 7 feet between a pair of vehicles. This heritage of testing under more demanding conditions helps to maximize the safety of the demonstrations we are giving this week.
One of the problems for automated highways is to merge cars in one lane at the entrance. Lane merge technology is ready, as it can be seen in this footage.
People are often curious about what an automated highway system is and how it would work. I normally describe it to them in terms of an automatic or electronic chauffeur.
Take control. Take control. On the road. Take control. I'm going out there. Automated drive in the road. Take control.
On an automated highway facility, you as the driver would drive to the entrance ramp in much the way you drive to the entrance ramp of a toll road today. And at that point, the control would be handed over to the automatic system, which would then do the driving for you. And when you reach your exit point, then you would resume control and continue driving until you got to your destination. This makes it possible for you to drive without paying attention to what's going on in the roadway. It lets you make use of that travel time to do whatever you want.
William